2. So this is our last of frontal appearance. I don't see Rajesh around. In principle, he said he would be willing to do a tutorial if the Hilbert space is not empty. This depends on you guys, if you have questions on that or not. Okay, please, Sergei.
Okay.
Close us.
Yeah, sure. So, as the last speaker, I also have the time to thank the organizers. I enjoyed this school many years ago when I came as a student. And I feel I've learned quite a bit also now. I'm coming another time. So, okay. So, well, what I was planned to do in this last lecture will be some mixture of some final comments on long strings and also a few words about short strings. So let me start with long strings first. Yeah, I think one thing I forgot to say, well, maybe say last time, we were discussing these numerical coincidence for that coupling Q, coming both from lattice data, from thinking about integrability, and from the bootstrap. And just I wanted to say that in terms of lattice data, there is a straightforward way to say what the coincidence is. Namely, I was drawing the spectrum of states, and there was spin 2 state measured from the lattice. It goes like this. Spin 0 state, which roughly goes like this. This is 3-level approximation, where they're all degenerate. And that coincidence is just a statement that if one compares it, but if one compares this data with just pure Nambu-Goto calculation, that pure Nambu-Goto calculation gives larger splittings. So this coefficient Q tries to undo the splitting which one gets. The contribution for pseudoscalar, it tries to undo the splitting which one gets from the Nambu-Goto. Can't quite succeed because the particle is massive, but it does it partially. Okay, so also, so from discussion we had so far, there are kind of two different expectations which one might have coming from what the serial of long string, what it does at high energies. Well, one expectation is again that to some extent some subset of observables is controlled by this approximate integrability. If one thinks it's not a coincidence. Well, on the other hand, if one thinks about a Wolfschild theory as a theory of 2D gravity, then in gravity one expects, doing high energy scattering, one expects to find black holes, or something like black holes. Well, and also associated copious particle production, right? So, basically for the purpose of this discussion, I'm thinking about black hole as a kind of some semi-classical configuration which describes high energy scattering in gravity. And so the question is kind of how these two match together and what these black holes are. And there is a project for the answer. And it was kind of almost spelled out already, but let me say it explicitly. Namely, let's think. So in this theory of 2D gravity, we know we have insight from gauge theory side of what are the kind of high energy degrees of freedom, right? So kind of there is third expectation, kind of piece of knowledge about what happens at high energies, namely that at high energies we should see perturbative QCD, in particular partons. And so thinking in these terms provides, I think, natural starting viewpoint about both where this proximal integrability is coming from, and we'll briefly mention it, but let me repeat. And also, what is a candidate configuration for black holes in this theory of 2D gravity?
You're choosing patterns because you don't want to say quarks and gluons? You want to think of something else? Or?
No, well, actually, if I talk about Purian Mills, we can, yeah, it's really gluons.
I thought you took a position between Feynman and Gilman.
No. It's really gluons, right? Well, and if it's really not QCD what I'm talking about, but adjoint QCD, right? So it's gluons or adjoint quarks and squarks, if one add them. And from that point of view, as we already said last time, so one may think about long string as an interior of the like heavy quark meson, where these heavy quarks are separated very, very far apart. And then high energy degrees of freedom from QCD viewpoint, considering talking about scattering of high energy excitations, that corresponds to taking two of these, well, it's Young Mills, and it's just really taking two gluons whose color is shielded by the string, so which live inside the string, and colliding them together. And then again, from intuition about asymptotic freedom, one can draw a cartoon of what one expects to find in this collision. Right? So they approach together, then they collide. So some collision happens, but at high energies, so first of all, they don't really care that there is string attached to them because energy is much larger than the string tension. And furthermore, not much happens because the series is free. So they just overshoot, and one gets kind of now this configuration. But because we work in the planar limit, the string is still there.
So these are adjoint.
Yeah, these, well, in pure glue, these are literally gluons, right? But in adjoint QCD, these are adjoint quarks. Yeah, these are some adjoint matter, right? Exactly. And then, yeah, they keep traveling for a while, but then one need to wait till because now in this configuration, unlike this configuration, now the string tension acting on this adjoint is not compensated on both sides. So now they move with acceleration. So after time for the E times the string length squared, so after time proportional to the collision energy, they get stopped, turn back, and eventually one gets back to this picture when they just separated. So, well, and now kind of in this cartoon, I started with two particles and ended with two particles. So kind of that's seems to match well with this approximate integrability picture. And also note this time delay, which I get here, that's exactly the same time delay which one gets in Nambu-Goto language, thinking about, there it was coming from saying, well, high energy excitation of string corresponds to taking just string longer, and kind of the proper length of a string is, again, is proportional energy. And this geometric calculation gives rise to the same time delay, but the underlying picture is quite different. In particular, there is a physical difference between result of the scattering. So in Nambu-Goto language, the scattering corresponds to total transmission, while here it is total reflection. So the same underlying physics, which gives rise to the same time delay, but the result actually is somewhat different. And that actually may be a hint of the reason why this integrability can only be, it cannot be exact, because if I think about theory with different flavors, so of course if I have only one particle, like in D equals 3, then there is no way to distinguish between transmissions and reflections. But in a theory with, if I have more than 2 particles, like always in D equals 4, if I introduce additional adjoint matter and also translate in particle excitations like that, then there is transmissions and reflections are different, and in particular, so one can take, for instance, a theory with 2 quarks, add some massive quark and consider scattering, consider a situation like that, when these 2 particles have different masses. Still, from this picture, one expects that there will be reflection, but on the other hand, for different masses, reflections are incompatible with integrability, because that means there is a momentum transfer. So kind of maybe there is some that's kind of this picture has in it some underlying physical reason why kind of confinement is not friendly with integrability. But I think I think the question is open, and it's interesting to think about options of confining theories which would be integrable in this sense. This picture provides a natural candidate. So that semi-classical configuration, which has been just drawn here, that looks like a natural candidate for black holes in this theory of 2D gravity. Again, for black holes in zeroth order approximation, I understand some semi-classical configuration which describes high energy scattering and in gravity. And in particular, it's interesting exercise where working on it now with Sasha Detlik is here. Yes. So one may expect if starting with this configuration, well, it looks like it has part of the physics which is present, which is required for particle production. There is this long period of time where these 2 endpoints move with acceleration. So it looks a lot like some UNRO type setup. So from this picture, one actually one expects that the end result of this collision will be not just these 2 partons which are being produced here, but from this period of time when they move with acceleration, there will be also probably the large amount of soft quanta produced. So that would be kind of analog of Hawking calculation for these black holes. And I think that's work in progress. That's what we're doing now. I think it will be interesting.
What would be the soft part?
Well, if it's literally the Young-Mills, dimensional Young-Mills, these are like Nambu-Goten modes of string, which are the same as soft gluons. But kind of in this picture, one thinks about hard gluons, one thinks about just this point-like objects, partons. And soft gluons, one thinks about them, they're just soft excitations of Nambu-Goten strings. And basically the exercise is, it's very similar to kind of these calculations with moving mirrors. So one has this gluon moving here, and it's kind of like a mirror, which, and actually, kind of the idea of the calculation is that if one really thinks about this as a gluon, then when we start from, let's consider the collision of two soft gluons. 2 soft gluons, we can either think about them as 2 Nambu-Goldstone bosons and do Nambu-Goten calculation, and that gives rise for this matrix. We can calculate it is low energy approximation, so it can be calculation like this. But on the other hand, one can go kind of to a boosted frame when one is boosted a lot, and then one thinks about one of them as a kind of particle point approximation, and another becomes still very ultra soft guy. So it's a little bit like Hopf derivation of the shock wave phase shift with gravity. So so from that point of view, one kind of knows, well, by matching these two results, one knows that for soft modes propagating on this background, there is some phase shift which they experience when they go. So it's not ideal mirror, but actually it's mirror which is characterized by certain phase shift. And that's the calculation which we're doing now. We take these two mirrors which move over accelerated trajectories like this, and so one expects from here that there will be some spectrum of particle produced. Yes?
In this zigzag shape, is there a large derivative at the fold? At the zig?
Well, yeah, so in the approximation, yes, it is literally. That's why I'm describing, kind of strictly speaking, Nambu-Goda description breaks down here, but the idea is to be able to describe this. Instead, I'm kind of describing the zigzag from the point of view of soft modes. I'm describing it by some effective S matrix, which characterizes how soft modes go through this.
As you're thinking of strings, these are strings, right? For you. Well, now they are not strings anymore.
Well, this is string.
Yes, so if you're thinking, I'm wondering, do you expect to get things similar to what Amati, Ciafaloni, and Veneziano did? Or
No, but that's different because they were talking about scattering of just say, two close strings, and here this is a scattering on the whole sheet of a single long string. So it's a different setup. Even though, incidentally, it is intriguing that this time delay which one gets here, of course, it's this S matrix. That's exactly the same S matrix which describes also in Transplanckian like scattering, leading iconal scattering in high-dimensional gravity. I don't know what to make of it, but why that's the same S matrix. But that has probably there's nothing deep about that. But
you're not going to discuss that, but you would hope to see some kind of format.
Well, there is other hope at least to see some kind of because there is some kind of the part of the spectrum which is in some sense universal, which is because indeed there are some assumptions here about what happens at like hard energies, but that the soft part of the spectrum, which is kind of controlled, roughly speaking, by something like the size of this maximum size of this zigzag, that should be approximately universal, and then indeed, kind of again pushing this black hole analogy to extreme, one may hope to find a regime when it's really becomes some resembling thermal behavior. And maybe that's too optimistic to expect. Well, but again, I think the statement that the bullshit theory in large and limit described by some version of 2D quantum gravity, that's almost kind of rather non-controversial. 2D gravity is weird, so it can be that the spectrum is not exactly thermal, but at least one expects to, like from this intuition, one expects to find lots of particles produced there. So that's yeah, and that's again. So when I was saying last time that there could be a reason why confinement is not friendly with integrability, it's kind of this kind of intuition that there is some semi-classical dynamics here, which naturally leads to particle production. So maybe integrability cannot be exact. And well, actually, there is yet another. I couldn't resist not mentioning that. I already brought up some pieces of numerology in my yesterday's lecture, but now I will. That will be real numerology, what I'm about to write now. But I feel there is something to that, which is again about this kind of conflict. That there is some tension between integrability and confinement. Namely, let's look at these two formulas. So one formula. So in the very first lecture, we wrote this amplitude for annihilation and also higher amplitudes for particle production in Nambu-Goda theory, which arises at one loop. So this is the formula. That's for annihilation, but that's over 60. There was a reason to separate factors like this. important one here is upstate. So that's one formula. And another formula is this one. So this is the formula for one loop beta function in QCD in the presence of NS scalar adjoints and NF while unjoined fermions. And of course, kind of one cannot ignore the fact that 26 minus 4 is equal to 22, and the number 22 not that often appears in physics. So the question is there any explanation between two pieces of, between this numerology, and can one formula leads to, that's a leading contribution to particle production on the string worldsheet, and that's contribution to violation of leading this violation of conformality, which eventually leads to confinement. Well, and at least can one cross-check that it's not completely crazy to compare these two formulas coming from these contributions, because one, kind of, as we already discussed here, right? So the intuition is if you start with Young-Mills theory, and if one adds extra, say, unjoined fermions or adjoint scalars, then one expects, and that can be done very explicitly, say, 2D adjoint QCD, that one sees very explicitly. One expects to find additional states on the string worldsheet, which corresponds to kind of the fact that now this Spartan can be taken not a gluon, but rather like one of these quarks and others. In other words, I can now use also these kind of operators to construct my string excitations. So one can start with a series. So when one starts with a series with adjoint quarks and adjoint fermions, then one expects to get additional corresponding scalar or fermionic degrees of freedom on the string worldsheet. And for scalars, it's kind of obvious, right? Because adding the scalar from the string worldsheet point of view at leading order, it's like adding an extra dimension. So the fact that it's 26 minus d appears here, adding the scalar does translate, does shift this coefficient in the same way. For fermions, it's somewhat non-trivial calculation because one needs to work out like this coset construction with an additional presence matter and work out how these fermions are coupled to worldsheet degrees of freedom. But at the end of the day, one gets that again, it matches. So kind of the modification of this formula in the presence of particles with the same kind of quantum numbers with respect to Poincare, which one expects from wild fermions in gauge theory, it shifts this coefficient in the same way. Well, which we kind of know because for n equal 4 superior Mills, of course, where there are both scalars and adjoint fermions, this vanishes and this vanishes. The theory is integral. Yes.
One is in wild speculations.
Yeah.
There is the Bank-Zaks point. Could this somehow be related to a description of the Bank-Zaks point?
Yeah.
Well, this point of view, when you raise an S, you just lose confinement, and then this other point of view doesn't even make sense. So it's not so clear how you
Yeah.
approach that.
Yeah, I'm not sure.
Once you lose confinement, then
You
what
could be
is
in the
this?
window, maybe?
No, but also,
But yeah, there is still a string even when you lose confinement, so yeah, maybe so.
yeah, I'm not sure. Also, I'm not sure whether it's numerology or not. But I think.
Is something that intrigued Sasha Poligo from the beginning.
Oh, yeah, I don't know. I know that Arkady Zeitlin kind of was intrigued by this. They had some paper in the 80s, but he was thinking about it different way. He was thinking more starting from UV. So here it's really two calculations being done, both done in QCD. One is high energies, another is low energies. I didn't know that also. Yeah. Okay, maybe.
We definitely knew that 11 comes out as 26.
Right. Yeah, and 11, well, that's a rare number to appear in physics, right? So, well, it's also a number of dimensions in M theory, but I don't think I don't think we need to try to relate that element. I think that one is different, but but here, well, I don't know. Also, number of pi's matches. Yeah, that's because both are one loop effects. Yeah. Anyway, I personally I think there is a relation. I think kind of if like sometimes I'm getting questions. So when do we celebrate? When we can decide? Okay, when there's two confining strings. So my personal answer would be when I understand where this is coming from. Maybe, well, because it's hard for following reasons. For instance, this argument with quarks and fermions, the most naive thing would be to say, oh, it's some kind of anomaly matching, right? Because those are some anomaly coefficients. But it cannot be that, because, for instance, when you have in gauge theory, when you're introducing quarks and fermions, even if kind of one adds zero mass to them, which is not even clear as invariant meaning, on the worldsheet they're not translating exactly massless degree of freedom. So it's not an exact statement. It's kind of approximate statement where on the worldsheet one thinks about these guys as approximately massless. And yeah, then kind of, and this is really effect in the deep UV. This is effect in the deep IR. So the only kind of project of the answer which I have in my mind how it could be that the same effect appears in both in UV and the IR. It's related to this physics. So that so what it tells us that the kind of the fact that the particle production here at high energies, it comes from this long time process. It tells that the full S matrix for this whole story is kind of it's factorized. It's factorized in the hard piece, which becomes trivial at high energies, and then there is some factorization theorem which describes it kind of this long-term process, and that factorized piece which leads to soft particle production. So that somehow this factorization may be responsible for the fact that it appears both in the UV and IR calculation.
Yeah, but this picture makes sense also in 2D and 3D, of course. Well, the beta function is only 4D. So
Right. Yeah. No, that's another reason. But I agree. Yeah.
So, Sergei, I mean, the corrections to the first expression are always still multiplied by 26 minus d, right? The higher powers of S and so on.
You mean in? Well, it's not. It's not a. There is a. So what I wrote here, that's a 2 to 2 amplitude, but there is just the whole set. There is 2 to n amplitudes, and all of them are proportional
to
2.
This is exact.
Yeah. Right. Well, it's correct. It's exact in sense. That's the only universal piece which is out there. Of course, there are corrections. Higher the corrections to 2 amplitudes.
Mm-hmm.
But
no, I was just wondering, is there anything to compare to the 2-loop beta function?
I was also wondering about that, but I didn't manage to find anything. Right. Anyway, so it is what it is, and maybe somebody in this room will eventually find an explanation or explain. Well, I don't know if it's numerology, then it's numerology. Just forget about it. Coming another peculiar property of this zigzag configuration is the following, which kind of I think makes this comparison. Yeah, because another kind of one objection which one often hears to comparing these zigzags to black holes. Well, where is horizon here? Kind of, and well, here in some sense we're starting with it's the opposite situation to what happens in gravity. In gravity, kind of at the leading order, there is no time delay, and then it's subleading. The particle production is associated to time delay. So here in this description, it's already time delay appears as the leading order, and so one doesn't need particle production to get a finite time delay. But there is some aspect. Well, again, for me, black holes really, as I said already, it's a device in gravitational theory to calculate what happens in high-energy scattering. So in that generalized language, of course. But there is another interesting aspect of this zigzag story, which is the following. So let's think. Well, let's just talk about the scattering kind of in terms of potential. We have 2 particles which scatter in this way, and that corresponds to describing the scattering in terms of this potential. And this potential, it has quite unusual property, if you think about it. Namely, from on-shell point of view, well, meaning from the point of view of calculating S matrix, it's the same as a potential for kind of scattering two identical particles. And that's how we can think if I have, say, string in D equals 3, where I have single Nabu-Goldstone boson, then, and that's in the language which we're using up to now, that's how we're just thinking about. So we have Nabu-Goldstone series here at low energies, and with scattering we have single Goldstone boson. So we calculate an S matrix of conventional particles, which are identical. Well, however, if you have a quantum mechanics like this, then kind of off-shell, in terms of describing what happens in intermediate states, this is not a quantum mechanics which corresponds to two identical particles, because for two identical particles, one expects to find potential something like that, which is on the half line, right, rather than on the whole line. And this is not kind of a technicality, this difference, because this potential which I was drawing, this e to the is, already said that this behavior, exponential growth at infinity, is not compatible with conventional QFT locality. So for instance, one way to phrase it is if one takes this potential, this is phase shift, sorry, and one would try to solve the inverse scattering problem with this phase shift. Then, well, usual assumption in the inverse scattering problem that when one does it, that again, there is some polynomial behavior at infinity. And here it is exponential, which is related to non-locality of this theory. And as a result, with this kind of phase shift, it's impossible to solve the inverse scattering problem on the half line. So the fact that this theory lives on the whole line, it's a necessity to get this rapidly growing time delay. And so what it tells us that this theory, so even though so from the point of view of on-shell variables, it looks like theory of identical particles. For its kind of off-shell description, it's really, well, it doesn't live in a conventional Fock space. So in other words, one way to think about this potential, which is related to the zigzag picture, is that if you do high energy scattering, then there is additional kind of pocket of space opens in between, which is exactly kind of this part of the zigzag, which is being stretched here. And that, I think, has kind of some resonance, resonates with how we think about black holes, right? It's some region of space which is created as a result of scattering. Well, and also, by the way, this tells us that Wolfschild theory provides a counterexample to Weinberg statement in his QFT textbook, right? Because basically Weinberg teaches us that the moment we do quantum mechanics plus special relativity will lead to conventional quantum field theory, meaning that it's dynamic. We're getting dynamics in Fock space, right? And the fact that here kind of off-shell dynamics happens not in the well, it's not the dynamics of identical particles, is related to the fact that actually it's not in the Fock space, and that can be made very precise. Again, it's a joint QCD. One can make QCD2. So a joint QCD2 with heavy fermions, one can make this very precise. Namely, as we already said many times, what we call Wolfschild theory, that corresponds to a single trace subsector, which is generated by, well, in case of QCD2, there are no dynamical gluons, so the only thing which you have, if you have additional, say, adjoint fermions, is a single trace subsector, which is generated by operators like that. Then in two dimensions, one can, as usual, I can fix, say, some axial gauge, and then integrate out completely the gauge field, and one gets some effective Hamiltonian, which describes fermion interactions, and then one just can calculate explicitly matrix element of this Hamiltonian between these kind of states, and one gets very explicit Hamiltonian describing Wolfschild dynamics, but this Hamiltonian, it acts not in the Fock space, it acts in the space of well, particles with infinite statistics, right, with of distinguishable particles. So kind of this, this one, right? So what's called Q-ons, but infinite balls of statistics, which is just basically the Q, but with Q equals Q equals 0. Actually, I was listening to previous talk. I was wondering, well, is there any?
This is called the Kuntz algebra.
Yeah.
Right.
It's
And then, of course, it's very simple from gauge theory perspective. It's just simple fact that we have color ordering, and that's what leads to distinguishability of a particle. So, it's kind of amusing system, which, from the point of view of on-shell data, it looks like a conventional S matrix of usual. So in that sense, well, Weinberg is always right. So he also right here. So then the on-shell dynamics here it lives in a conventional Fock space, that's as we were discussing here. But off-shell dynamics, if kind of it can be defined, it should be defined in a different space, not in a Fock space. So which, and of course that's closely related to the zigzag story, because the zigzag is just a statement that kind of one compares ordering of particles on the physical space versus their color ordering. That's where zigzags are coming from. So we see that the appearance of the zigzags is closely related to expected kind of non-local property of this theory of shell. Okay, so okay, good. So let me now come to the last topic, which I wanted to say a few words about, namely a few words about short strings, or glue balls, right? In the context of pure Yang-Mills, and that's well, that different context for this question, but basically Zero's other version of the question. So let's say one day we'll understand everything which can be understood about long string dynamics. Yeah, by short I mean kind of they're all close, but it's really winding number 0. So if we're thinking about the long strings that in my terminology were strings which are wound around a compact circle, and the limit when circle size is taken to infinity. Short strings, the conventional glue ball states, conventional closed string. And coming back to kind of QCD motivation, QCD, well, we mostly care about these guys. We don't really care much. We don't have this circle apart from when we're on the lattice. But naively one would think, okay, if I know everything about long string, then short strings you kind of made of the same stuff. Yeah, you take the same string, just glue it differently. So one would hope that it should be possible then to say something about short strings, or glue balls, if one understands theory of long strings. But to make it precise, it is hard. And in general, I don't know how to kind of go, even if I kind of have exact S matrix on the whole sheet of a long string. I don't know how to go from that piece of data to the spectrum of short strings, because one can ask what is the finite volume spectrum of that theory, but that gives me spectrum of excitation on a string wound around the circle. So for kind of usual, say, bosonic string, one can go from that spectrum to spectrum in the short string sector, just essentially plugging, analytically continuing winding number and going to winding number to 0. But, well, actually, we know, as I said, that doesn't work for glue balls. Just even in terms of counting the number of states, there is a mismatch, so it cannot be that. So I don't know how would I proceed to go between these two pieces of data. But one thing which one can do, and that's useful in particular, so we saw in 4 dimensions, for instance, there was this massive particle on the whole sheet of a string. In 3 dimensions, one doesn't find any additional states on the whole sheet of a string. One would think there should be kind of these additional particles which appear on the whole sheet of long strings, they should also appear in the spectrum of glue balls. So very, well, again, if one thinks about, say, meson as a long string stretched between two forks, if there is additional massive excitation, that tells us that there is additional exotic meson, which is obtained by adding that excitation. So one should be so kind of understanding the spectrum of short strings also and comparing it to actual lattice data or maybe even actual real world data. It's a way to check some of like our assumptions in addition to looking at the lattice data for long strings, check our assumptions about excitations on the long string, or maybe even predict new particles.
Just for blue balls, but for meson.
Yeah, also for mesons, right? Yeah, exactly, right. Yes, and the practical way to do it would be, I think the natural thing to try is to do lat J expansion, namely starting even like let's start with mesons. So that's kind of one of the first pictures which one sees in Green-Schwarz-Witten. So if there is, if it takes open string with lat J, then it can be approximated as the rotating Rhodes solution, and that those states they're supposed to describe leading rigid trajectory, and the lat J is a large and semi-classical, so one expects that to be a good description for lat J mesons, and then one can start quantizing around these kind of solutions, and that way construct at least part of the global spectrum. And in particular, if there is additional massive particle in a series, that means it's not Nambu-Goto series, there is additional massive particle, and there will be additional states, excited states, additional like subleading rigid trajectories associated with the presence of this particle. So that's a path which one can follow. Turns out there is a subtlety here, which I think we are close to resolve how to deal with this. That's the work in progress with Gabriel Cuoma and a number of students at NYU. The subtlety is the following, which is it's not often appreciated that this very first picture in Green-Schwarz-Witten for rotating string with Neumann boundary condition, actually it's quite from effective field theory viewpoint, it's quite subtle what happens here, because well, this solution which I wrote here, that's the solution for a string which rotates in the 1-2 plane. Tau, where sigma goes from -1 over omega to 1 over omega, and this omega is related to 1 over square root of j. So in the limit, in the lat J limit, one gets long string, and actually it's long and slowly rotating string. So that kind of goes well in the intuition that it becomes more and more semi-classical, this geometry. However, to see that there is a subtlety, one can, for instance, look at the induced metric on this whole sheet, and the induced metric takes this form. Sigma squared, d tau squared plus d sigma squared. So the endpoint corresponds to the place where this prefactor vanishes. So it's kind of, from the point of view the observer sitting in the middle of a string, this is a point of infinite redshift. So it's a little bit like black hole horizon, but it's also not a black, because because it's only G00 which vanishes here. So not only it is a kind of point of infinite redshift, but also if one calculate the induced curvature, for instance, then it blows up at this point. So in spite of the fact that the string gets very long, at the endpoints, this solution is singular. So from the point of view of effective low energy theory, kind of we don't notice it when we quantize strings in string theory. We actually don't notice that we resolve in taking Neumann boundary condition. We resolve in something which is really naked singularity from effective field theory viewpoint. And actually, I think that thinking in terms of this phase shift, so this redshift is actually useful for understanding much of the physics of this system. So, for instance, if I if I'm thinking in terms of effective field theorist, then I can now turn on also just not start doing normal Gotha. I can turn on high-dimensional operators. So, additional operators in particular, I can turn on the mass at the endpoint of a string. There's no symmetry, which forbids this mass. Yeah.
This configuration describes both a folded flow string rotating and
Right. So here I was talking about meson, open string, but yeah, but for closed string, it's kind of the same. In that way of thinking about it, well, in that picture, it's immediately obvious that there is a singularity here because there is a false singularity. But the singularity is present also in this case. So right. So for instance, what happens if one adds a mass term like that? Well, actually, if one adds essentially any higher the correction. So because if one adds even bulk correction, if one adds term r squared and in the bulk, so they all kind of lead to a similar effect. Namely, as a result, the string, for concreteness, I will talk about the mass, but as a result, string, it changes the boundary condition. It's not Neumann anymore. So this range changes, and so now this scale factor at the boundary, it's not exactly 0, but it's something of order. In case of the mass, it's m ls squared times omega. So in the limit of small omega, which corresponds to large j, there is still a very, very large. So the geometry is not singular anymore. And if mass is large in string units, actually the curvature gets smaller. But of course, for gluons, for light quarks, we expect the mass. Well, the mass is of order string units. Actually, by this mass is really effective fields theory way of saying what constituent mass of quarks is. I think that's the way to think about that. But in all these cases, no matter what, still the physics of the system is that there is a large j, so you have kind of this long string, but there is large redshift factor in large j limits. There is large redshift factor between endpoint and between these, and that's kind of so for instance, Kobe was doing these kind of calculations a lot. So if one calculates, say, the correction to leading Regge trajectory for this massive guys, then one already at the classical level, one starts getting some weird powers like this, like j to 1/4. So the expansion is 1 over j expansion in presence of the massive points. It goes not in integer powers of 1 over j, but there is this j to 1/4 power, which appears here. And thinking about this term, it provides an intuitive picture for what happens. So there is a cutoff scale, which is locally LS, but then there is additional redshift factor between physics at the endpoint and kind of physics in the middle. And so by a redshift, and so essentially that for long strings that creates additional scale in the problems. It becomes double now 2 different scales, and that's mu scale. That's exactly what controls kind of that's the origin of this fractional powers. It's really kind of LS redshifted by this redshift factor. So it kind of that makes a little bit. It makes a little bit subtle to define this effective string theory. Well, actually, Simeon Hellerman kind of has a proposal to do it in Palczynski-Strominger formalism. But to be honest, I don't fully understand the logic. But actually, it looks like probably he's right. Probably what he does is correct. But we are now kind of almost done completing this in Nambugota language. Also because what we want to do from the purpose of calculating global masses, we want to calculate the spectrum of excitations. And well, Simeon never tried to do that, and in Palczynski-Strominger formalism, it's a little bit more complicated. Nambu-Goto language is better suited for that. It's kind of analog of static gauge.
What happened in the case of flow string?
Right, so that's, yeah, Simeon actually, from Simeon viewpoint, he thinks that this case is somehow much more complicated than this one, but it's more subtle, but on the other hand, from effective, if you effective field, yeah, there's also close strings, right, but still there is, this M is kind of, it's effective operator which appears in the boundary. From effective field theory perspective, I don't see big difference between these two. So I have, basically here I have two like point-like objects connected by one string, and here I have 2 point-like objects connected by 2 strings. But if I know how to describe this, there are more parameters there here, so probably there is kind of some transmission S matrix with like some which characterize how things go here, there. But in terms of, if I really know how to describe this system as effective field theory, I should know also how to describe this one, and kind of this M, it's just, well, it's effective boundary operator, so it's some defect in this theory, and which also get generated there. And also, as I said, one doesn't, so at the technical level, the problem that theory breaks down, that there is an X singularity at the endpoint, manifests in the fact that if you start with a Nambu-Goto term and start adding high-dimensional corrections, then all of them, so the naive derivative expansion breaks down close to the boundary. So I don't need necessarily, if this M is not large, if M is of order 1 over less, then I can write the mass, but I can also write R square, bulk R square term, and because curvature blows up towards the boundary, effectively from the point of view of how it modifies solution, it plays exactly the same role. And that's a challenge, that all these operators, which in the bulk, they are in different order in 1 over less expansion, close to the boundary, they contribute at the same order. So that's why one need to kind of reorganize. That's not really a part of kind of
Square root of
sorry?
why you don't get a odd number.
Well, that comes from these redshift factors. This funny power comes exactly because that can be understood by, so the LS, because LS sets a local UV cutoff scale, but that local UV cutoff scale is the same here and here, but then here it gets redshifted by the factor which comes from here, and that's why this funny polarity. Well, of course, if this mass itself is of order LS, then at the end of the day it is a less here, but still this funny power of J can be understood this way. Well, I think we're at the stage when we kind of understand what happens here, and I think we agree in a different language with what Simeon proposes. But it looks to us then we don't see obstacle to kind of generalize this logic also to this case. It's technically a little bit different, but that's where we're now. But yeah, how much time? Yeah, I do have some more time, right? So let me finish it by telling instead what we done earlier, which was kind of naive. Well, it was naive version of this approach, but it worked surprisingly well. And by the way, yeah. So this picture, thinking in this language from QCD viewpoint, it also looks kind of natural because I think it's kind of also related to what we were saying before about these zigzags. It suggests that kind of the proper way to think about glue balls close to rigid trajectory. It's more like two adjoint gluons connected by a pair of strings. So this picture makes a lot of sense also from that viewpoint. The exercise which we did a while ago was the following. So the motivation was, well, exactly we were kind of trying. So that's n equals 3. Eventually one wants to do it in d equals 4, but that I think requires better understanding of all these issues. But at d equals 3, so based on lattice data for long strings, so it looks like the statement is that strings d equals 3 strings in d equals 3 and meals, they're described just by kind of theory in the Nambu-Goto equivalence class, meaning one doesn't add any additional massive particles on a world sheet. And we wanted to check this statement looking at the spectrum of glue balls, because again, the expectation, if there are additional massive excitations, they should show up. So we tried to do the following calculation, which actually worked better than expected. And actually, this calculation, as we realized later, it wasn't the most obvious one to do, but it works better than the more obvious one. But the calculation was the following. So we want to describe, so we have this piece of information that long strings are described by theory which kind of leads an order Nambu-Goto action plus something else, but no extra degrees of freedom on the world sheet. And we want, from that piece of data, we want to get these quantum numbers of global states. And we made the kind of several assumptions. Some of them are I think well motivated, some other less well motivated. One assumption was the following. So what does it mean to have a bullshit theory that you don't have massive states and you have only kind of one left mover and right mover? Well, it means you have set of left movers, set of right movers, and the full Hilbert space of closed strings. That we're talking about closed strings now. Closed strings that should be sum over levels, just like in critical string theory, of left moving Hilbert space times right moving Hilbert space. That's, I think, because level matching condition is really, one motivation for that's how it happens in critical strings, but really level matching condition is just a statement that the shift invariance for closed strings is that generates a gauge transformation, so that level total momentum should be equal to 0. So I think that looks like a natural kind of invariant statement, what it means to have a theory without any extra massive modes. You have just left movers, right movers, and you have that. So that piece was rather unambiguous. But then the second piece the second step was the following. That was, again, motivated by what we know from critical strings. Namely, we said, well, this Hilbert space of left and right, they're the same, and they're given by Hilbert space of open strings. And to understand Hilbert space of open strings, let's just do what I was describing so far. Let's take this classical rotating rod solution in Nambu-Goto theory, so ignore all these subtleties with the fact that really there is singularity, just Nambu-Goto theory with Neumann boundary condition. And at large J, we can quantize perturbatively around this solution, and that gives certain Hilbert space. And then let's use that Hilbert space for what we call H open. So incidentally, I'm not 100% sure it will work, but at least in this picture, it looks like there is one naturally gets similar structure, right? Because here, again, one closed string looks like really two open strings with additional matching condition. They're glued here. It doesn't look like exactly the same level matching condition. But my hope is that will be kind of more system. Then they will produce the same answer. So it will be systematic way to kind of derive this prescription. Here it was really ad hoc. It was just from the fact we know it works like that in critical string theory. So let's try to do the same way. Of course, and then kind of the expectation is, so of course, for critical strings we know, because for this calculation to be powerful, one needs to make some assumption about masses. For critical strings we know that, well, masses grow with n, and at each level there is a degeneracy. So for QCD, we don't expect exact degeneracy because there is no exact integrability. But so the expectation was, again, that's kind of a check of this approximate integrability, that one should find kind of multiplets of states for for glue balls measured on the lattice, which have quantum numbers which one obtains from this calculation have the correct multiplicities. So, but will be split somewhat, and then the goal of this effective field theory approach would be then to learn to how calculate these splittings perturbatively. That's what we're trying to do now. And of course, so this calculation which I just described here for open strings, it works only in the large J limit, and that was completely ad hoc, so because we didn't know there's no better thing to do, we said, okay, let's just take the same answer, which one gets at large J, and use it at all J's. And okay, and that leads to a set of predictions for, well, basically level by level. We're now getting predictions for quantum numbers of states. What quantum numbers are you talking about? So in the open string calculation, I have here, there is kind of J1 and J2. There is, because I mean, that's a three-dimensional series. So quantum numbers is J, which for massive particle, that's just J with respect to O2. That's the little group. And then there is parity and charge conjugation, but for parity only meaningful for scalars, because states with J not equal to 0, they come in pairs of opposite parity. So there is for scalars there are two parities, and then for J larger than 0 there is just charge conjugation. That's what we're trying to calculate, and the way charge conjugation arises here, charge conjugation usually it corresponds to reversing the orientation of a string. So it acts by exchanging left and right moving part of the spectrum. And by proceeding this way, one gets the following prediction for few low line levels. So for instance, well, this is the level, and this is what one gets. Like level equals 0. Here one gets plus. And by the way, that's where these low line levels, of course, that's where this prediction is completely ad hoc, because that's J using large J expansion at J equal to 0. So here one gets 1 tensor 1, and that gives 0 plus 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 0 minus minus plus 2 plus. So here in total there is 1 state. Here there are 4 states in total, because there are 2 polarizations here. Then this is 1, this is 2 here. So these numbers, they come from quantizing around long string. So that's 0 plus 2. Here one gets 2 times 0 plus plus 0 minus minus plus 2 plus plus 2 minus plus 4 plus. Finally, let me write the very last one, because something new happened there. So here we have 9 states. So at the level number 3, and equal to 3, one gets 0 plus 1 plus 3, tensor 0 plus 1 plus 3, and that's 3 times 0 plus 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 2, 0 minus minus plus 1 plus plus 1 minus plus 2 times 2 plus plus 2 minus plus 3 plus plus 3 minus plus 4 plus plus 4 minus plus 60 plus 6 plus. In total, 25 states. And then we start comparing the lattice data. Well, to be honest, kind of when we were building these ansatz, there was already some lattice data available. So actually, kind of, we already looked at these few states. And by the way, this prediction of tensor square product is already, without doing any calculation, it's already somewhat non-trivial. It tells that you expect to find groups of glue balls with multiplicities which are squares of integers. So these states were already there in the existing lattice data, and kind of they were 1, 4, 9 states, which are rather well identifiable, and they work. They agree with what happened here. Now, for n equals 3, at the time, there were some of the states were there. And actually, well, at the time there was a contradiction, because there was a claim, basically, in lattice data, what they saw 1 spin 1, I think, and 3 spin 3, rather than here there is 2 spin 1 and 2 spin 3, and that's a very robust prediction, so that odd spin states, which first time appear at this level, that they should come in pairs of opposite C parity. That's very robust prediction of this calculation, just because odd spin state come from taking different spins from here and here, and then you always have pairs of C plus and C minus. So it's very, very hard to get something different from the string picture from this picture. Right, exactly. The trouble with lattice is that on the lattice you have Z4 rather than O2 in there, so in general they determine Z4 quantum numbers, and actually from some of the states they just work mostly Z4 quantum numbers, but in principle one can, that requires dedicated simulation, one can, but basically by taking good lattices and construction operators which are kind of approximate rotations of O2 rather than full Z4, one can check whether the states, which spin they belong to. And that kind of, the claim was, after that being done, the claim in the literature was that they finding 3 spin 3 and 1 spin 1. So with Mike Tepper, a student at NYU, we kind of redid that, and also we did the analysis of the full global spectrum in D equals 3 with the goal really to determine O2 quantum numbers. And then it worked. So one does find these 25 states. Some of the states were not seen before, and it turns out that kind of there was misidentification for spin 1 and spin 3. So it worked. So kind of this calculation, somewhat miraculously, it works very non-trivially, and it works in the regime where kind of because it really for starting with low spins. So that's a little bit puzzling, because really that assumption that something taken at large J can be extrapolated at 0J, that was totally wild. That's the only thing which we could do. But well, in my view, that's again goes in the direction of confirming this idea that the theory should be thought of as some deformation of integrable model, because for integrable theories, that's quite common that kind of semi-classical calculation produces exact results. And so here, that large J, that's kind of semi-classical calculation doing large J, and also this provides, if there is indeed integrable theory like that, so that provides, and then you deform it, but the spectrum is a set of quantum numbers. It's kind of a discrete set of data. So it's kind of that provides a concrete definition of what we mean that the theory is in the same equivalence class, that the quantum numbers of states are the same as in the.
So for an integrable theory, does this decomposition become exact or not?
Well, that's the hope. We don't know the integral. Well, we have a candidate integral model for long strings, but we don't have a description as a short string spectrum. So the hope is that integrable theory produces exactly this spectrum. Then it's less mysterious why large J expansion gives, the large J expansion gives exact result, and then kind of it makes precise the statement what it means for theory to be deformation. So that you introduce splittings but didn't change the quantum numbers of the state.
For any integral model, if you just use TBA, do you get this product structure or not necessarily?
Well, but you see, because we don't know how to use TBA for this calculation, because it's not a finite volume spectrum of that theory. It's rather, and moreover, actually, there is a bit of a kind of puzzle here, because say for critical strings, as I said, like in the simplest examples for Poissonic strings, for instance, right? So the spectrum in the sector with 0 winding number can be obtained from the spectrum with winding number 1 just by analytic continuation. But it doesn't work here because, like, even at the level of open strings, because for So if I have just some got a theory in 3 dimensions in D equals 3, then if I take the string like that wrapped, like long string wrapped around a compact circle, then at level 0 I have a ground state, and at level 1 there is a single state, which is, well, just with momentum 1. While here, when I look at this spectrum, that at 0 level open string I find zero, spin 0 global, but at spin 1, at the level 1, I find a doublet. And that's actually how this calculation, because that's where usual critical string fails in non-critical dimension, right? Because you don't, that's where you find mismatch, that's why you need d equal 26, because there you find the massless particle, and the number of states here doesn't match the dimensionality of the representation of massive little group, and instead you need to use massless little group. However, this prescription, starting from lot j and pushing it all the way to j equal to 0, so that prescription produced 2 states for us, and that's indeed what is needed. So somehow it's different from what one usually does, and it works and fixes this problem at the first level, which is the reason why we're getting, why critical strings are interesting, right? But they produce for us massless gravity, right? And massless gauge theory. So we don't want that for QCD strings, and that prescription of doing the calculation, it gets around this, but also it shows that something interesting going on here, that in the number of states of a theory in the winding sector is different than the number of states in the sector without winding. Yeah, maybe it provides.
Equals 3 is sort of critical.
In what sense?
Well, now, there's only one transfer flow,
Well, there is no. Yeah, so there is no anomaly on the long string. From the short string perspective, it's a little bit more tricky, because, well, actually this kinematical cancellation which I was discussing for the long string, it's reminiscent also what happens in light cone gauge quantization, right? That's probably what you're referring to, that if one does light cone quantization, then there is this commutator, which is usually anomalous, but at d equals 3, it's still equal to 0, because I equal to j. So that's kind of suggests that, okay, that cancellation which one finds in d equals 3, maybe it's reminiscent of this thing, and at the technical level, it is reminiscent. But it's what we are finding here, it's definitely different theory. Because, for instance, yeah, so indeed, there was a paper by Townsend and Zvichescu who proposed, say, okay, let's take d equals 3 strings, do light cone quantization. Then they argued that there is no, well, just this argument, that there is no anomaly. So let's calculate the corresponding spectrum. And what they found, first of all, even in terms of multiplicities, that spectrum, it's still, yeah, for the usual reasons, it has, at the level 1, it has 1 state rather than 2 states. So that's not the quantization which we're getting, and the not quantization which corresponds to Young-Mills. But also it's not the quantization which corresponds to Young-Mills for the following reason. What they found is that when they calculated the helicities of resulting states, and they found that there's necessarily states, for excited string states, with irrational helicities, which is in d equals 3 in principle it's possible, so it's a kind of some theory of anyons. But it definitely sounds like some kind of anomaly from the point of view of this calculation, because you start from classical theory, which is invariant on the Poincare group, but then as a result of quantization, you get a spectrum of the infinite cover of the Poincare group. So for me, it sounds like a situation similar to chiral anomaly, where kind of at n larger than 2, the anomaly appears in the commutator of local currents. But then n equal 2, there is still a global anomaly. And I think this light cone quantization, I think it's still the fact that they're getting anyons. It's suggestive.
So madness damping is considered string filter, string scattering, light cone gauge. So found an anomaly also at the vertex of the splitting string, which also disappeared.
It also disappeared.
So even at this level, it's not enough for interacting strings.
Yeah, and also in the control gauge, you do find the potencies.
Right, yes.
So certainly there are anomalies also
Yeah.
at equals 3.
so at least this calculation what we are doing here, it's not just that. But the fact that on the long string there is that S matrix which is non-linearized, that's probably related to, that's why kind of my gut feeling is I already telling that that's probably these integrable models we're talking about, they're not fully consistent string theories. That's one of the reasons for that. But they still but it kind of still looks like there are some useful approximations for the full story. But there is a reason why really you can build.
The anomalies are harder to see.
Right. Yes. But yeah, that's something to be understood. But again, so this prescription is more is smarter than that, because using this, even kind of if one just does like concatenation at d equals 3, that produces even forget about like values of helicities. That just at the level of counting the number of global states, one gets it wrong. One doesn't get 2 states at the first level by this prescription does it. So yeah, well, I think.
So this hasn't been pushed beyond that.
You mean this? Well, we have partial data for n equal 4. There are 64 states there, so it's a lot of states, and it gets harder and harder. So but in lattice data we don't have, and because also these are quite heavy states. So there is no. I think the best way to say it, there is no it's in the cases where one can do good comparison, it seems to agree with what we have. There is no clear contradiction. But also, it's also true that as one goes to higher and higher excited hadrons, because just from the sheer fact that there is this number of states grows so dramatically, the splittings, they become larger and larger, so it's harder and harder to distinguish these different levels. So this approximate integrability, yeah, we're discussing it earlier with Offer also. Yeah, it's again a manifestation of UV-IR mixing, right? So because naively one would think, oh, looking at the heavy hadrons, that's where you probe UV. But actually, it's the other way around, because heavy hadrons, most of them are very long strings. These are very IR states. So the most UV part of the spectrum is this one, where things work. But of course, just looking at the spectrum of globals, you cannot go to infinitely deep in the UV, because the lightest global which you have, it has string scale. But the fact it works for low line levels, at some point later on, this comparison, it doesn't become very useful probably, because one can try to compare some gross features of the spectrum, like spectral density or something like that, but really the levels now start overlapping and because of the splittings. But I think what would be interesting to do, it would be interesting to learn to calculate splittings using this effective field theory and to see whether one can reproduce those. For instance, in d equals 3, I told you the S matrix has also, for long strings, there is a correction to the phase shift. It's S plus S cubed, and that coefficient is measured. So when one understands how to do this effective field theory calculation, one should be able to check whether, because that correction should manifest itself in the splittings between the states level by level. So one should.
Where is that correction measured?
No, that correction was measured from, that's what I mentioned yesterday, just from looking at the strings, for long strings, looking at the splittings between different states. For long strings, one can measure correction, like one can measure this operator on the voltsheet, and so we can use now that value in principle, we can plug it into calculation of global spectrum and to see that works. So that can be done and should be done, hopefully it will be done, but of course the fact that at least at the level of quantum numbers, it works so remarkably well where it shouldn't have to work. It suggests still there is some nicer story going on here. And yeah, maybe one last thing. So I mentioned it already, but let me make it more precise. So recently we also did another calculation. Namely, we did the calculation. And initially, frankly speaking, we thought that it would give the same result, but just this one is simpler to do. Namely, instead of going through this two-step process take an open string and then tensor square in it. We just did the same. We took this rotating rod solution in closed strings, in Nambugota closed strings. Again, ignore the fact that there are singularities here, but just using Nambugota, calculated the spectrum of glue balls. Again, starting from large J and interpolating all the way to J equal to 0. And to be honest, initially I thought, when we were writing a paper about the spectrum first, doing open string calculation, I thought that it will be the same, that it should be equivalent. And what we got that proceeding this way, so if one looks at the leading edge trajectory, that's leading edge trajectory, the two calculations, they agree in the vicinity of the leading edge trajectory, but at highly excited states, they start disagreeing. So this calculation actually, it overcounts, it produces more states than actually one finds in the actual spectrum, and then one finds from the first calculation. So it shows that it's somewhat non-trivial that what we did initially worked, and the hope again, but that we didn't check yet, that kind of maybe the proper way of doing, so there may be some subtle difference between doing this naive calculation and this calculation kind of with two endpoints, because for instance, this calculation doesn't even reproduces the levels don't come as multiplets of integers, so it doesn't have this tensor square structure. This kind of naive effective closed string calculation doesn't even reproduce that. While in this picture, and also I think the tensor square structure is really should be correct, just level matching. So I hope that we'll be able to reproduce this by doing properly the closed string analysis in this way. That's well, one should say something like what it means. Kind of, it's somewhat non-trivial to kind of glue two strings together here. But yeah, so we're not there yet. But I hope it can be done. But at least it shows that there's no contradiction. The two calculations agree in the regime where effective field theory expected to work. They agree in the vicinity of the leading edge trajectory. And incidentally, one can also compare that to light cone quantization, which is another way. It's wrong quantization, but again, it should all different quantizations, they should agree in the semi-classical regime because it's wrong only at the quantum is at one loop order, and that it produces yet another spectrum, which actually this one overcounts the number of states, light cone undercounts the number of states, but again in the region in the vicinity of leading edge trajectories, they all agree. So the disagreements they start appearing for highly excited states. But it's quite non-trivial that prescription which we used initially, that it reproduces kind of, it works essentially in this region, which is, that's a non-trivial. Also here, but in other words, starting from very, very low excited states with small spin. Okay, I think that's probably a good point to wrap up.
The thing you didn't have time to discuss, right, is if it's d equals 4, you actually need this extra degree of freedom to agree with the length, or you have some evidence there.
Well, at d equals 4, well, I guess you're referring to the fact that d equals 4, yeah, so if one were to repeat the same at d equals 4, then one expects, for a long string, we have this extra 0 minus state, and so one expects to also, it will appear now in the spectrum of glue balls. And actually, yeah, one thing one can check in d equals 3, that if one adds extra degree of freedom with smallish mass, that leads to dramatically larger number of states, because there is exponentially, there are much more states. Clearly, glue ball spectrum strongly supports the idea that there are no extra massive modes here. So for d equals 4, well, it's kind of tricky to do because this is a massive mode with mass of order less. So we cannot really do the calculation at the same level just by counting quantum number. We need to do proper effective strings here. Effective.
You can see whether,
but right.
even and out,
Yeah. So, but still, what we did in d equals 4 so far, we did the following: we just repeat analog of this exercise. Assume that there is no extra massive mode, And let's calculate the spectrum which one predicts from Nambu-Gotta. And then one gets 0 line 0 plus plus. Then remember, well, one gets analog of this, but d equals 3 at first level. But if one compares to actual lattice data, then roughly, well, in the same group of states, one finds actually states at level 1. It seems to kind of roughly match what one finds Nambu-Gotta, but there is additional state which is 0 minus plus, and that's very, very hard to get from the taking this tensor square calculation. But on the other hand, it's exactly matches what one expects. So if one just thinks naively, take this 0 plus plus and add on top of it massive state with the quantum with this parity of quantum numbers, then it exactly gives rise to this state. So in the spectrum, there is a candidate state clearly which corresponds to it in that. So in that sense, it nicely agrees. And who knows, maybe one day one will see particles like that also at LHC. Okay, one expects it also for mesons, right? So for any meson, basically the statement that for any Regge trajectory there should be additional one. Well, I think that corresponds to what people call like gluonic, exotic hadrons with extra gluonic excitations, right? Because these axionic particles, that really some gluon. So, but that's really work in progress. Yeah.
That's the end.
I wanted to show you this. This is what you wrote.
Ah, yes.